Hi everyone, welcome back to MATA35. This is the last week of lectures. So there's today's lecture and next Wednesday's lecture, and then the final exam is a week from Monday, which is really scarily close. But we have now completed enough material, if you take a look at the course calendar, we've now completed enough material that we know enough to be able to actually model real biological systems that are often of interest to people. And so that's going to be the theming of today's class. So today we are going to be talking about some of the basics of epidemic modeling. This is obviously super topical, but we're going to start with building up a basic model from first principles and using all the techniques that we've been covering in this course to understand what happens with these models. So now the big question is, of course, what are we trying to model? So many of you have seen lots of these graphs, too many, in the news. This is a graph of new reported COVID cases in Canada over the course of the pandemic. And now, we might wonder, well, we have all this data. How can we actually... Oh, yeah, so it does look like it's going back up. So the Delta variant, turns out it has a higher infectivity rate. It has a higher R naught, which we're going to actually cover in today's class. And so it is on its way back up, which is really quite scary, but we'll see what happens. So, but anyway, we have all this interesting behavior here, right? So we have some function of time. So we start out with, well, obviously 0 down here, and then all of a sudden we jump up, and then it seems like we're going down and up and down and up and down in all these waves. So now, what causes the progression of these epidemic curves? And that's what we're going to be trying to build. We're going to try to build a model today that tries to capture some of the behavior of these epidemic curves. And more sophisticated versions of these kinds of models are what we actually use in practice to try to model, well, the progression of the pandemic. So if people are saying, well, we think that we're in trouble because this might go back up, well, the way they predict that is by using epidemic models that are more sophisticated versions of the types of things we're going to be covering today and next Wednesday. So, we want to try to model this curve. Well, we know how to model curves, right? So let's start by just thinking about the various assumptions that we have about how epidemics spread. So, we're going to start with a single assumption. Let's start with a very, very simple model. Assume that each infected individual infects other individuals at a constant positive rate beta. So, I mean, this is basically what we mean by something that's infectious. Well, it starts with one person, and then you encounter someone else, you cough on them, and then all of a sudden you have 2 people who are infected, and so on. So let's start with this model and see what happens. So we're going to try to see what happens with this biological model when we just add one single assumption. Each infected individual infects other infected individuals at a constant positive rate. So, well, we need to set up some variables. Let I of t be equal to the number infected at time t. So the number of infected individuals. Well, what we're saying is we have this infection rate. And so that's the change in the number of people who are infected, right? So what we can say is that the change in the number infected as a function of time, so dy dt, the rate of which that changes is equal to beta times I. So it's the rate of change is some constant times the current number of people infected. If you have 1,000 people infected, well, then next week you're going to have bad times. Versus if you only have 1 person infected, well, next week will still be worse, but not necessarily so bad yet. So what happens when we try to solve this? So this is, of course, a differential equation. I dot is equal to beta I. Excuse me, sorry about that. So I dot is equal to beta I. So we can rewrite that. I dot minus beta I is equal to 0. Well, we know... yes, we have a good question. But what about people that recover? Would this be assuming that no one recovers? Yes, you're jumping ahead of the game. This would be assuming that no one recovers. We're going to start with a very simple model and then see what goes wrong, and then we're going to try to then basically fix the model by adding more and more assumptions. But let's just try to figure out what happens with this particular model with just one simple assumption. So we have a characteristic equation. So we have lambda minus beta is equal to 0. which of course implies that lambda is equal to beta is the only eigenvalue. And so I of t is equal to c times e to the beta t. We can solve for the constant because we know that by just saying, like, let's say that there's some, at time 0, there's some number of infected people. And so you get c e beta times 0, which implies that c is equal to I of 0. And so I of t is equal to the number of people infected at time 0 times some exponential function of this growth rate. Now, obviously, if beta is negative, well, then things decay. But if beta is positive, well, you get exponential growth. So let's focus on the initial months of the pandemic. So I've zoomed in here on just the initial couple months, and well, let's see what we want to try to build a model. So we need to know what beta is, right? Let's jump ahead. What's wrong with this model? A, is the model too simple? B, is it impossible to determine a good beta? C, does it not reflect the data? Or D, all of the above, or none of the above? So what do people think? Okay, so we have a good mix of different guesses. So some people think A, some people think C, some people think D. Well, the answer is this is, of course, there are many things wrong with this model. But in particular, one of the things that isn't wrong is actually you can find a good beta. And so D is actually not the right answer. The correct answer here is either A or C. Because you can use regression to find a good value for beta, or even just trial and error. So if you have different values of beta, you're going to get different exponential curves. So you might get something like, if you have a very low value of beta, you might get an exponential curve that goes like that. Actually, I should redraw that because it has to start off not at 0. If it starts out at like 1, you might have an exponential curve that goes like that. Or if beta is higher, you might have an exponential curve that goes like that, or even faster. So you can actually use linear regression or use regression techniques to find a good beta. This is one of the things we studied in nonlinear regression using Python. We're not going to go over that right now, but just you can find good betas based on the data. Now, there are a couple problems though, and the big one is that this model is too simple and it doesn't reflect the data because although it looks like you do have some exponential curve initially, that exponential curve doesn't model the data afterwards. The model doesn't take into account the fact that you have a finite population size. This model would suggest that eventually you have an infinite number of people infected, which of course is not possible because, well, you don't have an infinite number of people on the planet. So this goes past the carrying capacity of the population for a disease. So let's try to fix that. So let's give another assumption. Another assumption might be there's a total fixed population size n, which is equal to I of t plus s of t, where s is the number of susceptible individuals. So if that's the case, well, we still have I dot is equal to beta I, n is equal to I plus s, which together implies that I dot is equal to beta s is equal to n minus I, and s dot is equal to minus I dot, which is equal to minus beta I. So what kind of model do we have here? Well, this is actually a two-compartment model, S to I. So we have susceptible individuals going into the infected column at a rate beta I. Now, does this fix the problems from the previous slide? Or, let me reset before you guys reply. Okay, so it looks like people think this doesn't fix the problems from the previous slide. A few people say maybe. Does someone who said no want to put in chat why you think this doesn't fix things? So what's wrong? We now have a total fixed population size n, and we're then we're saying that some number of people go from susceptible to infected. Okay, so someone asks, it still seems a bit too simplistic. And yes, it is still a bit too simplistic. But it turns out that there's actually an even worse problem, which is that we created these two compartments and we're moving things from one to the other. It still doesn't have recovery. That is true. It also doesn't have reinfection. But even more importantly, you'll notice that the equation for I is exactly the same. So this doesn't fix anything because we implicitly, as biologists, thought, oh, well, you're moving people from S to I. But that's not what the math says. The math says you're taking some, the math allows S to go into the negative. So it allows you to have negative people. And so therefore, this is not physical. So let me show you what happens. So we still have I dot is equal to beta I, which is the exact same equation we had before. So we can just solve for I. So then I of t is equal to the initial number of infected times e to the beta t. Nothing changes because we didn't change the equation at all. And then when you solve for s of t, that's equal to n minus I of t. So that's I not e to the beta t. So when you plot this out, what you get is, well, you have some finite population size n, and you start with some number of infected. Let's use blue here. So you have some number of infected, and it grows exponentially. And you have some number of non-infected, let's call this the green one here, susceptible, and that goes the exact opposite. But you'll notice that it goes into the negative. And this is a problem. So model still goes off to infinite infected. And even worse, negative susceptible. Okay, so this doesn't quite fix things. And the reason for this is even though we put in this assumption that there's a finite number of people in the population, we didn't say that the number of people couldn't go negative. And in fact, we have to change the infection rate if we want. Why does it go past n? Oh, because this formula doesn't stop. So this is just the exponential growth formula. And so we didn't put in an assumption that you can't go past n. And we didn't put in an assumption that you can't go into the negative. And in fact, those kinds of assumptions are hard to enforce because I give you some function and it might go positive, it might go negative. And so instead what you need to do is you need to change the function so that it doesn't go past n or doesn't go below 0. So that's one of the hard parts about building a model, which is that you have some behavior that you know you want, or that some behavior you know you don't want. And then you need to figure out some way of getting the math to behave that way. So like, we know that we don't want more people infected than the number of people in our population. That's not possible. We know we don't want a negative number of people who are susceptible. That's also not possible. But we need to somehow make the math reflect our intuition about how actual biology works. So it turns out that people have thought about this, and there is one assumption that does fix the problem of going off to infinity and below 0. And this is a commonly used assumption, which we've talked about a little bit in this class. So we have a modified assumption. So instead of just the assumption that each individual infects some number of individuals, the modified assumption is that the infection rate is proportional to the average number of times an infected individual encounters a susceptible individual in the population, assuming random encounters. So basically, if an infected individual comes across another infected individual, well, that doesn't increase the number of infected individuals because they're both already infected. And so when we write out this formula, well, we have this proportionality constant, so that's just beta, times, well, the average number of times an infected individual, so encounter some of those, that's beta times I, and encounters a susceptible individual in the population. So what's the chance that if you encounter a random person in the population, well, that they're susceptible? Well, it's the number of susceptible people divided by the total number in the population, so that's times S divided by N. So this is now our new infection rate. So this is the infection rate. We have a slightly modified version of this two-compartment system. You have Si, and you have beta Si over N as your new rate of moving people from S to I. And so on, you get we have N is equal to S of t plus I of t, per usual. And then we have, you have S dot is equal to minus beta Si over n, and I dot is equal to beta Si over n. So it's not obvious yet, but it turns out this assumption will actually allow us to prevent things from going past n. And we can see this qualitatively using a phase line argument. So I've just copied over the equations over. And our phase line argument, well, let's try to solve, get the phase line. So we have S is equal to n minus I, which means I dot is equal to beta I divided by n times n minus I. So we've rewritten it as a function of just one equation. So since we've rewritten it as a function of just one equation, now we can solve it using phase line methods. And I'm going to go ahead and call this I dot f of I. And note that this is a single variable ODE. So what are we going to do? Well, let's try finding the equilibria. So what are our equilibria? We have 0 is equal to I dot is equal to beta I over n times n minus I. So one of those terms has to be equal to 0, which implies that I is equal to 0 or I is equal to n. So we end up having two equilibria based on this model. And what does it look like? Well, you have one equilibria here at 0 and one equilibrium here at n. And we want to figure out, well, the stability of these two. So how do we do that? Well, if you take if you do a sign analysis, you'll find that in this region, f of I is equal to something negative times something positive, which is less than 0. In this region, f of I is equal to something positive times something positive. And that's because we take each of these two pieces and we see whether or not those are positive or negative in this region. That's greater than 0. And here, f of I is equal to something positive times something negative, which is less than 0. And this is here the I-axis. But n can't equal 0, right, without making it undefined. Oh, we actually have to be slightly more careful about that. So yes, but you can rewrite this actually as, yeah, you're right. So n can't be, if n is equal to 0, then things get super weird. But let's go ahead and solve it as if we allowed n to be equal to 0 for the purposes of, no, yeah, sorry, n can't be equal to 0. N equaling 0 means that you have no one in your population, since n is the total number of people in your population. And so, yes, n can't be equal to 0, because if n is equal to 0, then that means you have a population with 0 people, and so there's no possibility for infection. But I can be equal to 0. So the number of infected people can be equal to 0, even although n can't be. So when we do this, we get a phase line. So here we get, these are the arrows we get. And then we immediately can say, well, this is unstable, and this is asymptotically stable. Actually, we can even say more than that. So we've done this phase line analysis on the entire model, but we can go further and basically what just happened? Let me fix that. Keep on switching into the wrong slides. There I am. So it turns out that we can get rid of all that and all this. Because, of course, the number of infected individuals can't be greater than the size of our population, and it also can't be less than 0. But luckily that doesn't matter, because with this model, if you start anywhere over here, you're just going to go to n, and then you're asymptotically. You're not going to go past it, because that's an equilibrium. And so this model doesn't actually ever go above n, and it doesn't go below 0, which is what we wanted. Does that make sense? So this model does stay within the range of 0 to n, which is good. Assuming you start between 0 and n, you stay within 0 to n, which is what we wanted. And we don't have to worry about the cases where it starts outside of 0 to n, because that's not physical. And so what we have is a model that, well, everything goes to n, or the number infected always goes to n. Now, of course, this is also a little bit unphysical, because we don't include anything about recovery. So basically, this would be a disease that once you get, you can never recover from it, and well, that's just it. So if you had a disease like that, well then yes, of course, it would just spread to everyone in the population, because no one would ever recover. let's actually take this opportunity, though, to, instead of doing this qualitative analysis, let's solve this SI model exactly. So what method should we use? We've covered a lot of methods in this class. Come on. What method should be used? Okay, so we have some a u-substitution vote. We have some votes for separation of variables. Yeah. So it turns out that we can actually use any or all of these methods. So they'll all work. It'll depend on what exactly you want to do. Because we're going to take this opportunity to use this epidemic model to review some of the material we covered in class, I'm actually going to solve this two different ways. Because just as an opportunity to well, practice two different ways of solving it. So let me start with the more complicated version. So this is going to involve things like Bernoulli ODEs, integrating factors, and u-substitutions. And maybe also using Ansatz method. And then in the moment, we're also going to solve it using separation of variables. So we're going to solve it two different ways, just so that we get practice doing that again. So let's write this out. So this is I dot is equal to beta I minus, will the method be constant for every model? I don't know quite what you mean by that question. Could you rephrase it? Depending on depending on parameters, that can change the methods that you have to use to solve a model. That can happen. No, we're going to do the more complicated method first, and then we're going. Oh wait, sorry. I wanted to do the more complicated method. Actually, no. Well, let's use the separation of variables first. It's an easier method, so let me change up the ordering. Let's do separation of variables. So this is equal to beta I times 1 minus I over n, just by multiplying the 1 over n through. We are skipping ahead a slide. I think this is a better order since this is the easier method. So then what do we get? We get di dt is equal to beta I times 1 minus I over n. We can separate the variables. So separate variables. And what we get is di divided by I times 1 minus I over n. Because remember, n is just a constant, so is equal to beta times dt. And now we just have to, let's do a little bit more rewriting. Let's multiply both top and bottom by n on the left. So n over I times n minus I di is equal to beta dt. Now, this is the part where it's going to get a little bit more complicated, which is we're going to actually use partial fractions now. So remember, we studied partial fractions way back at the beginning of class when we were doing integration, since that's what we're going to do now. We need to integrate n over I times n minus I. So this is a complicated integration because we need to split it up into two pieces. So what we're going to get is, we're going to get some constant a divided by I, plus some constant b divided by n minus I, di is equal to beta dt. And when we do that, well, we need to solve for that. So we know a times n minus I plus b times I is equal to n. Well, that's because we need this to be equal to that. So we need those to be equal. When we solve this, we get an plus I times b minus a is equal to n, which implies that a is equal to 1 and b is equal to 1. And so indeed, if we plug those numbers back in, 1 over I plus 1 over n minus I, that is actually equal to n over I times n minus I. di is equal to beta dt. Well, now we've separated out by fractions, we can do a integration on both sides. And we get natural log of I minus natural log of, absolute value of I minus natural log of the absolute value of n minus I is equal to beta t plus c. We can combine these together using the rules of logarithms. Natural log of, I'm going to multiply by a negative sign on both sides actually to make this a little bit work out nicely. So let's multiply by -1 on both sides. And I'm going to combine these together. And so then you're left with natural log of n minus I divided by I is equal to minus beta t plus c. If we take the exponential of both sides, we get n minus I over I is equal to c e to the minus some constant, some other constant. We're playing fast and loose with our constants now. E to the minus beta t. And if we, of course, notice that this thing here is equal to n over I minus 1. That's the reason we flipped it. And so you're left with n over I is equal to 1 plus c e to the minus beta t, which implies that I is equal to n over 1 plus c e to the minus beta t. Okay, so that's one way of solving it, which is you can use separation of variables. And then you get the how did the addition of two fractions become a division? Oh, because that's one of the rules of natural logs. So remember that log of a plus log of b is equal to log of ab. And also that log of a minus log of b is equal to log of a over b. So this is one of the rules of logarithms. Okay, so this is one way you could solve it. It's a little bit complicated because you have to do this weird partial fractions thing and do a little bit of manipulation with the logarithms. We have other ways of solving it, so let's talk about using seeing this as using integrating factors, u-substitution, or things like linear systems. So I'm going to resolve this a completely different way, and what we're going to do is we notice that I dot is equal to beta I minus beta I squared divided by n. We rewrite this, we get I dot is equal to, I dot minus beta I is equal to minus beta I squared over n. And this here is a Bernoulli ODE, which we talked about in the section when we learned about integrating factors. And if you go back to our notes and how we solve the Bernoulli ODEs, what you can do is you can multiply by minus I to the minus 2. And then we're left with, let's see, let me call this di dt times minus 1 over I squared plus beta over I is equal to beta over n. Let's do a u substitution. Let u be equal to 1 over I, and du be equal to minus 1 over I squared di. And then what we get is du dt plus beta u is equal to beta over n. And now this here is a first order linear equation. So remember, this was the technique we used to convert a Bernoulli into a first order linear. And now once we get to this point, you can use an integrating factor. The integrating factor would be e to the beta t, multiply that out, and you get an exact integral. I'm actually going to solve it a slightly different way. So you could use integrating factor, so could use integrating factor. But it's actually slightly easier in this case if we just solve this as a inhomogeneous linear first order equation. And so we can write out the characteristic equation, which is lambda plus beta is equal to 0, which implies that lambda is equal to minus beta. And so then you get a homogeneous system, solution, c e to the minus beta t. And you can use an ansatz. We're going to guess that the particular solution is going to be, well, some constant a. And then we know up dot is equal to 0. When you plug that in to the equation in the top of the right-hand side, you end up getting that beta a is equal to beta over n. So a is equal to 1 over n. So u sub p is equal to 1 over n. And so then u of t, the general solution, is equal to c e to the minus beta t plus 1 over n. Well, we know that u is equal to 1 over I, and so therefore I is equal to 1 over u. And so I is equal to 1 over c e to the minus beta t plus 1 over n. Let's multiply both the top and bottom by n and rearrange it slightly. So n is equal, this is equal to n over 1 plus c e to the minus beta t. And of course, you could also solve it using integrating factors to turn it into an exact equation and then use that process. But basically, we have many different methods that all work for solving this system of equations. Since I didn't actually use integrating factor, I'm going to rewrite this as Bernoulli, ODE, u-substitution, and characteristic equation. Okay, so there are a bunch of different ways of solving the system of equations, but we have this equation at the end of the day, and notice that it is the same between, we get the same answer, which is as we'd hope. Sometimes it might look slightly different because your constants are slightly different, but so long as your constants are things you can switch around as parameters, it's still fine. So what does this look like? Well, this turns out to be something called the logistic growth equation. So the SI model, which is the susceptible infected model, has logistic growth, and it starts out like the exponential over here on the left, but then it hits your total population, and then it flattens out. Okay, so this is an improvement, right? We've gone from going off to infinity and having non-physical results to just having something that is physical because you're bounded between 0 and n. But it still might not be what you want. So we no longer go off to infinity, which is good. But we're still missing the downward part of the spiral. So now, instead of our original exponential model went like this. Actually, let me use a different color for that. Our original exponential model went like this. Our new model goes like that, or something like that, but it doesn't ever go back down. So how do we get the number of infected to go back down in our model? So what do people think? Should we add a recovery term? Should we add a mortality rate? Add an immunization rate? All of the above? None of the above? Okay, yeah, so you guys are right. Any of these will cause the number of infected to go back down. Or, I mean, well, that's not quite true. Immunization doesn't cause the number of infected to go back down. It just causes them to not get started to begin with. So either A or B would work in this particular case, though immunization rates are something we will care about in terms of keeping the number infected from going up to the maximum population size. So the answer here is A or B, but C is also relevant. Like, it doesn't actually solve this particular problem of going back down, but it is relevant in keeping it from going up. So we're going to start by talking about recovery. So there are different ways, as you guys have seen. What we're doing right now is we keep on adding on different assumptions or different terms into our model, and then we hope to try to recapitulate the behavior of the actual data that we see. And so let's try a couple different things and see what happens. So what if we have individuals recovering? So let's say that individuals recover at some rate gamma, but become susceptible to reinfection. So this model is, again, a compartmentalized two-compartment model. You have your S, you have your I, and you go from S to I at a rate of beta Si over n, and you go from I to S at a rate of gamma I. So this is called the SIS model because you go from susceptible to infected, and then you go from infected to susceptible, and so on. And it turns out that this depends a lot on both of these parameters, beta and gamma. So let's write this all out, and let's consider the different cases. So if n is equal to s of t plus I of t, let's go ahead and assume again that we have a constant population size, n, and we get s dot is equal to minus beta over n si plus gamma I, and we have I dot is equal to beta over n si minus gamma I. We can rewrite this a little bit because s is equal to n minus I, so let's rewrite it again as a function of just one variable. I dot is equal to beta over n times n minus I times I minus gamma I, or this is also equal to, if you write this, beta over n times minus, oh sorry, I did that wrong, that's just beta minus beta I over n minus gamma times I. Question, going back to the actual COVID cases graph, we started out with exponential growth. So when Canada started using more vaccines, can't we just switch our regression model with parameters? Yeah, so let's actually take a moment to go back to the original graph and talk about this. So that is actually one of the things people do. So like we started off with this exponent, and what that exponent is dependent on how quickly things spread. And then you add various other measures. So maybe you lock things down, and then the spread goes back down. Or maybe you're in some other place where the exponent goes up much higher. So one of the things you can do is you can do an exponential regression model and then just try to fit it into each of these individual curves. You don't get the overall behavior, but then you still get some prediction for the near future. So yes, that is something you can do. But unfortunately, an exponential curve will never be able to get really capture what happens as it goes back down. You can have exponential decay, but it isn't actually the same behavior as the going back down that you would expect with actual epidemic waves, which is a much more complicated phenomenon. But that's actually something we're not going to properly get to until next Wednesday, because that's going to involve, actually end up needing a two-variable model in order to get to that point. But let's first analyze this SIS model. So we have this recovery rate, and we hope that this is going to look something a little bit more physical instead of having at the end all individuals be infected. So one of the disadvantages of the logistic model is at the end of the day all individuals are infected, which if there's recovery is something we don't expect. What about exponential decrease? Does that exist? Yes, it does exist. But it turns out that the form it takes, in fact, we're going to see a little bit of that in a moment, or something like that at least. So once we have this SIS model with two different parameters, well, we have to consider both cases. So there are two parameters, beta and gamma. So there are three cases to consider, where beta is, what are your guesses for behavior in each of these? Let me reset. What about when beta is equal to gamma? What happens if the number of people who are, if the infection rate and recovery rate are the same? What do people think happens in this model? So remember, beta is your infection rate and gamma is your recovery rate. So does the disease die out? Does the number of infected go to a non-zero constant? Does the number of infected oscillate up and down with multiple waves? All of the above or none of the above? Okay, so a lot of people are guessing. So we have a couple of different guesses, which is good. It's good to have different guesses. So some people think the disease dies out. Other people think that it goes to some non-zero constant. Now, unfortunately, there are good arguments for both, but we really need to analyze it before we know the answer. It turns out that the math works out so that the disease just barely dies out. So the disease does die out, but it doesn't, but it does it not at a particularly fast. Yeah, so it does die out, and we'll see the math for that in a moment. Let me reset and ask you, what if beta is less than gamma? So what happens if the infection rate is lower than the recovery rate? Well, remember though, I just told you that it does die out even for beta is equal to gamma. So what do people think will happen when beta is less than gamma? Yeah, exactly. So when you have when the infection rate is lower than the recovery rate, well then eventually the disease dies out. And in fact, this is an example of you will see something that looks almost like an exponential decay if you like solve through the math for all of this. And lastly, if beta is greater than gamma, well then let me just go ahead and say bad stuff happens when beta is greater than gamma. So it turns out that okay, so it's not quite C actually. So the answer here actually is B. The number of infected goes to a non-zero constant. We don't have enough parameters to have a oscillatory behavior. So remember when we study predator-prey equations, we could have oscillations where the number one goes up and down as the other goes up and down. But in this one variable model, we can't actually have oscillating behavior, and the answer is that it goes to non-zero constant. We will see oscillating behavior next week when we discuss these two variable models, which are a little bit more physical. We just need to add more and more stuff to this model. But let's go ahead and start and just covering all three of these cases. So case one, beta is equal to gamma. So this is where your infection rate is equal to the recovery rate. So note that beta is equal to gamma, and so those cancel out. So this implies that I dot is equal to minus beta I squared over n. So let's just do a qualitative analysis. You guys actually have all of the tools you need to actually solve this explicitly, but let's just look to see what happens qualitatively. Well, what equilibria do we have? Well, I dot equal to 0 implies that I is equal to 0. So the only equilibrium is when I is equal to 0. Note that minus beta I squared over n is less than 0 for all I not equal to 0. So that means when we draw out the phase line, we only have a single equilibrium here at 0, and our direction is negative everywhere. So we have a semi-stable equilibrium. But of course, we don't really care about the stuff that's negative, and so it just stops at 0. So what this implies is that the disease dies to 0 asymptotically. As time goes to infinity, the disease barely dies out. So this would be an example of something that looks vaguely like exponential decay. Well, case 2 is a little bit interesting because you also get so this case isn't exactly exponential decay because you have this I squared term. In case 2, we actually get something that's similar. So in case 2, we have that, let me write this in 3 different parts, is equal to, why is it semi-stable and not stable? So that depends on how you define semi-stable and not stable, but here, if you have in theory, mathematically, if you had a negative number of cases, you would get, the number of cases would keep on getting more and more negative. And so mathematically, it's still not quite stable because you start with -1 infected individuals, then, well, it doesn't go to 0. From a biological perspective, this is stable because you only care about positive numbers. So from the perspective of the positive real line, this is stable. And this is one of the things where, as a mathematical biologist, you have to be able to go back and forth between mathland and actual, like, real world. In the real world, you don't have negative infected. In mathland, you can. But we just ignore that. But let's take a look at case 2. Here you have, we can rewrite this as beta minus gamma times 1 minus beta over beta minus gamma n. Oh, sorry, beta minus gamma n times I and I. So I'm rewriting it in this funny form so that we can then do a sign analysis of it. This is equal to f of I. When we find the equilibria, we get I dot is equal to 0, which implies that I is equal to 0, or I is equal to beta minus gamma over beta times n, which in this case is less than 0. Yeah, exactly. So in the real world, the previous model was good. But if you're in math land, you have to be a little more careful. So here we know that our other. Oh, how do we find the other I? So the other I is from here. If you set that equal to 0, you find that I is equal to beta minus gamma n over b. So I skipped a couple steps since we're running a little short on time. But it turns out that this is going to be beta minus gamma n over b. And we can do the same sort of sign analysis. So you should try plugging in numbers that are smaller or greater. And what you find is that you get this phase diagram. And again, this bit here is irrelevant because negative. And this here, we again get 0 as a disease-free equilibrium. It is a disease-free equilibrium, disease-free, asymptotically stable equilibrium, which is good. So we get the same advantages of. So we get the same set of advantages that we do when they're equal, when the infection rate is smaller than the recovery rate. Which should make sense, because, well, if you're not being infected as quickly, that's a good thing. However, we have the last case, which is the case here. Again, we can do the same breakup. So this is, again, equal to beta minus gamma times 1 minus beta over beta minus gamma. Oh, what happens on the left side of the BI part? Oh, that's all negative, so it doesn't matter. So we have an unstable equilibrium. So we have, this is unstable. But that doesn't really matter because it's negative. And this is asymptotically stable. But it will matter for this other part here. Where this, let's see, n times I, which is equal to some f of I. We have the same set of equilibria, because I dot equal to 0 implies that I is equal to 0, or I is equal to beta minus gamma over beta times n. But in this case, it's greater than 0, because beta is greater than 0, so now this other equilibrium is positive. And so we're left with a different phase diagram. And when we solve this phase diagram, we actually get not so great behavior. So we get beta minus gamma n over beta. And when you actually look at the sign analysis, what you get is that that's unstable and this is stable. Again, we don't care about this, but in this case, the other equilibrium is positive, and so we do care about it. And so we end up with an unstable equilibrium at 0. We don't want the disease-free equilibrium to be unstable, but it is in this particular case. And we have a asymptotically stable equilibrium here at b minus gamma n over beta. So we have an n, this is what we call an endemic asymptotically stable equilibrium of beta minus gamma n over beta infected. So when you have a disease like this, what happens is that the number of infected doesn't go to n. So your entire population doesn't stay infected, but you always have some small amount of your population that is infected. So diseases like the common cold, you might think to model using these kinds of models because you end up never going to 0, but you never go to n as well. So this isn't so bad, but you never get rid of the disease. And we can understand this a little bit by just looking. We've understood this basically by looking at the cases of the ratio between beta and gamma. When beta is equal to gamma, the disease dies out. When beta is less than gamma, the disease also dies out. When beta is greater than gamma, the disease persists. So you guys might have heard of R0 or R0. So in the SIS model, we call the ratio R0 the basic reproduction number of the system because it's the number of secondary infections beta caused during the infectious period 1 over gamma. So remember, the recovery rate is gamma, so the time you're infected is on average 1 over gamma. And so the number of individuals one individual infects while you're infected is beta over gamma. When R naught is greater than 1, the disease persists. When R naught is less than or equal to 1, the disease dies out. And one of the big efforts of public health officials during a pandemic is trying to get R naught below 1. Because if you can get R naught below 1, then the disease will slowly die out. If it's above 1, then it'll still grow exponentially at like some different exponent. There are many different ways you can do that. Some of them include lockdowns, others include vaccines, others include various other sorts of more complicated models where you have different types of interventions. So now, on Wednesday, we'll cover some more complicated two-variable models where you will get much more complicated behavior, including possibly oscillations. And with that, I am going to stop the recording, and I will see you on Wednesday.